We're now going to look at the tools that are available in Excel and MATLAB to find the roots of an equation. Now we've learned how to use the bisection method and Newton's method, and it's not that difficult to program that into either one of those into MATLAB or to implement them in Excel, which we've done in the previous videos. But because both of those programs have built-in tools for finding the roots of equations, we're going to concentrate on using those instead. Now within Excel, there are two tools, Goal Seek and Solver, that can be used to solve nonlinear equations. And in MATLAB, there's a function called fzero. So those tools all work for any kind of nonlinear equations. If you have a polynomial, there's a specific tool within MATLAB called roots that will find all of the roots of a polynomial. Now in supplementing those, we know how to graph things in MATLAB and Excel, and that could be a nice tool to use as well to find out where the roots are approximately, so that we can hone in on them with any of these other tools. So let's talk about Goal Seek first. With Goal Seek, we simply have our independent variable in a cell and our function in another cell, and we're telling Goal Seek to set the function equal to a given value, in this case usually 0, by changing the cell with the independent variable. Again, it's very simple to use, and we'll demonstrate that in just a moment. Solver can do the same thing, but it's a little more complicated, and it's very powerful tool though if we're going to find the solution to a system of nonlinear equations, which we'll do in the next video. Solver also can do a lot of things toward optimization, and we'll look at that a little later in the course. So let's look at Goal Seek. Here's the equation that we looked at earlier in the last video. We know that there's three roots to this equation, and to set this up in Excel, we simply make a cell for x, our guess value, and we put that equation into a cell for y. Goal Seek is available under the Data tab and the What If Analysis tools. I'm going to shift over to Excel at this point. And so you can see here's our value of x, our guess value, and here's the equation for y. And so we want to set this to y, this value of y equal to 0 by changing this value of x. Data tab, What If Analysis, and there's Goal Seek. So I want to set the cell containing y equal to a value of 0 by changing the value of the cell in x. And there's one of the roots, 5.6577. Now, we know that there are a couple of other roots. We'll show the graph in just a moment, but one of them looks like it's kind of close to -2. So running Goal Seek again with that guess value, still trying to set y equal to 0 by changing x. And there's one of our roots, -2.0764. And there was another root close to +2. Set y equal to 0 by changing x, 1.4187. And again, just showing those, and showing again that if we graph this, we can see where those three roots are approximately. So after I put in the value of 10 kind of arbitrarily, we found this root right here, but then the other two are close to -2 and +2, so we put those in as guess values to find the other two roots. Okay, so that's Goal Seek. Now in MATLAB, there's a function called fzero, and again that finds the root of a function starting with a guess value. So let's define a function, and we're going to use the same equation here. So we'll write a MATLAB function called fun1. And so MATLAB function, first line, first word is always lowercase function. Here's the output of the function. Here's the function name, and in parentheses, the argument of the function, or the independent variable. and here's that equation for y. Okay, so when you use fzero, notice that we have two arguments of fzero. First is the name of the function with that and sign before it, and the second is the guess value. So just like we did in Excel, we'll guess a value of 10, and we get that root of 5.6577, the same one we got in Excel. Now you can also, instead of a guess value, you can put a range of values, and so in this case we'll look for a root between x equals 5 and x equals 10. Of course we'll get that same answer. Now when we talked about the bisection method, we said, you know, the values of the function at these two have to have different signs for the bisection method to work. So if you use the range and you don't have opposite signs at the two endpoints, then it says you get an error. So that pretty much shows you that the bisection method is used by fzero when you set a range. Okay, as we said, making a graph is a pretty good idea because you know how many real roots are going to be and about where they are. So here's two equations that look almost alike. The only difference is that second term, minus 15x squared or minus 5x squared. But if I graph them, we can tell how many roots, how many real roots each one of them has. For the first equation, you can see it passes through the x-axis 3 times, 3 real roots. Equation 2 only has one real root, but we do know it's a third-order polynomial, so there are 3 roots. It's just that 2 of them are complex roots. Now, the MATLAB function roots will find all of those, whether they're real or complex. So the argument of the roots is an array that contains the coefficients of the equation. So looking at that same equation we've been looking at, the coefficient array, one from left to right, is 3, minus 15, minus 20, and 50. So going back this way, you always start on this end with x to the 0, or a constant. This would be x to the 1 power, x squared, and x cubed. So we put that in. Again, we'll just call it, assign it the value of a. So a is the array that contains the coefficient, and the command is simply roots of a, and we find those 3 roots of the equation. Now, for that second equation, again, very similar. We just call the coefficient array b in this case, found roots of b, and you'll notice in this case that first one is shown with a plus 0i, but of course that's a real root there, the minus 2.812, and then there are 2 complex roots as well. So again, roots will find all of the roots of an equation, both real and complex. So one thing to be careful of when you're defining the coefficient array, you notice in this case there's not an x squared term. So you wouldn't put the coefficients in as 3 minus 200 minus 100. That would be interpreted as 3 times x squared minus 200x. So you have to put in a 0 as a placeholder for the x squared. So our array looks like this: 3, 0, minus 200, 100, with a 0 in there to indicate that there is 0 times x squared. And when you run that, again, you'll find the roots command will give you the 3 roots of that third-order polynomial. You can combine those 2 lines there. In other words, roots of, and then the argument, again, is that array. And the array is just shown in square brackets like that, and you get the same answer. So those are the tools that are available in Excel and MATLAB. It's important, though, to remember that there may be more than one root. There may be no roots. So keeping that in mind, that when you come up with an answer doesn't mean that it's always the answer. So you want to check, you want to graph when you can, but it's as opposed to earlier when we found the answer to a group of simultaneous equations that were linear. We said if we find a solution, we know that it's the only solution. But remember, when you find a solution to a nonlinear equation, that it may not be the only one.